Welcome everybody. I am Philippe Michel, and I have the pleasure to chair this invited lecture by Emmanuel Kowalski. So Emmanuel Kowalski received his PhD from Rutgers University and then held a position at Princeton University and at the Institute for Advanced Studies, and eventually returned to France to take a professorship at University of Bordeaux. In 2008, he moved to ETH Zurich as an ordinary professor, where he is currently. In 2019, he was elected at the Academia Europaea. And besides its numerous seminal contribution at the crossroad of analytic number theory, group theory, and arithmetic geometry, Emmanuel is also the author of several books, some of which have become great classics. At the personal level, I am especially happy to introduce this lecture because Emmanuel and I have been collaborating since we were babies, basically, and we are still collaborating. So I open the floor to Emmanuel.
Thank you very much. So I will share my screen. And thanks a lot for the introduction. As Philippe says, we've known each other for a long time. We've worked a lot, including on the kinds of topics I'm going to discuss. And if there's a failure of internet on my side, you could probably just improvise and start from where I will stop. Okay, so I'm very happy, of course, to give this lecture on one of the topics I find the most fascinating in number theory, exponential sums over finite fields during this European Congress. So the part which is new, I will discuss a lot of historical results to try and present this topic in the context on which it arose and to highlight the main developments historically. But the part which is new that I'll discuss towards the end is joint work with Arthur Fauré and Javier Frezan. And it's kind of work in progress. There's a draft of what we're writing, which we made available just on the occasion of the ECM, and that we will take out at some point because there are still probably some embarrassing mistakes in the draft. But if you want, you have time to download it between now and the end of this lecture and the next few days. Okay, so what are exponential sums over finite fields? So these are some of the most simple mathematical objects you could possibly imagine. It's just a finite sum of complex numbers. Typically, the complex numbers have modulus 1. We might sometimes allow some variety with this, but let's assume for the moment they have modulus 1. So it's a finite sum of numbers of modulus 1, often roots of unity, but not always. But what makes these exponential sums of finite fields is two facts. First, the index set on which we sum will be either a finite field, like here I denoted FQ, a finite field with Q elements. So we'll use, in this lecture, for simplicity, I will mostly work with the finite field with P element, where P is a prime number. So Z mod PZ with addition and multiplication of residue classes. And the other thing that makes a sum of this kind an exponential sum over finite fields, in the sense that there is a certain theory that exists, is that the complex numbers we sum, these often roots of unity or sometimes something else, must have some kind of algebraic nature. And what does it mean to be of algebraic nature? Well, they are completely precise definitions, but they tend to involve a lot of complicated or deep algebraic geometric notions. So I will illustrate this in this lecture mostly by example, and like the following. So one of the most basic examples that arises already a long time ago is when alpha of x, the numbers that you sum, are exponential 2i pi f of x over p, where f is a polynomial with integral coefficients, let's say. So here we think of x as an element of z modulo pz. So in this case, we have to remark that whichever integer we use to represent it, which has the same residue class, will give the same value of the exponential, because exponential 2i pi Z is periodic of period 1. And to give a vague idea of what does it mean to compute an exponential sum like that, so here I have a drawing which represents the partial sums of an exponential sum of a special kind that I will discuss a bit later. It's a Clusterman sum. The blue dots are the partial sums when we represent the integers modulo. In this case, I think the prime is of the order of 100. So the integers from 0 to p minus 1 are used to represent the finite field. Okay, and so what you see is something that's quite chaotic. In that case, it ends at the end with a real number, which is relatively close to 2. And we'll explain a bit later why that is, in what way this is relevant to the theory. Okay, so to summarize, we are considering just finite sums of numbers, very often just roots of unity, and we are asking questions about what happens with these numbers. And the kind of questions that led to the discovery or the invention or first people considering these sums is quite old. So the history, I think, goes back at least, and maybe even earlier, but Lagrange is associated, I mean, the name of Lagrange is associated with so-called Lagrange resolvents, which he used to try to solve certain type of polynomial equations in the 19th century, early 19th century. And these very often were sums of roots of unity, not necessarily indexed by a finite field, but still sums of roots of unity, which were shown to have certain nice algebraic properties. They were solutions of certain equations, polynomial equations. Maybe the first really recognizable exponential sum of a finite field, and still one of the most important, are the Gauss sums. So these are denoted tau of chi and a. So there are two parameters. Chi is a multiplicative character of Fp. So that means it's a homomorphism of the multiplicative group of Fp with values in the complex numbers of modulus 1. And Fp star, I wish to remind you that by a theorem of Gauss, this is a group which is cyclic of order, of course, p minus 1. Okay, but we do not fix a primitive root of unity. We just consider all the possible multiplicative characters. And on the other hand, there's the E of ax over p, which is just exponential 2i pi x over ax over p. So we use the notation E of z for the exponential when it's periodic of period 1, which is very convenient for this kind of notation. So we are combining a multiplicative character times an additive character, because the exponential respects addition, and we do the sum over the finite field, or in this case, the non-zero elements in the finite field. And here there is an analogy which I want to immediately present, because it actually is very suggestive and is actually quite deep and leads to many developments or intuitions about exponential sums of finite fields. So if you think of summing something multiplicative times something additive, there is a function that we consider all the time in analysis. It's a gamma function, and at exactly the same shape, except it's an integral. It's a continuous sum, an integral of something additive, which is exponential of minus x. Here we cannot take something of modulus 1 because the integral would diverge. But we have an additive character times something which is multiplicative. So as a function of x, x to the power s is multiplicative. And then the measure dx over x is natural for integrating over non-zero positive real numbers, because it's invariant by dilation. Okay. So the gamma function can be thought of as being an analog of the Gauss sums, or the opposite. So to continue a bit with this analogy, I can use that to justify the definition of another exponential sum, the Jacobi sums. And I can justify that by looking at a formula which is well known for the gamma function. And it's a fact that most formulas that you know about the gamma function, they will have an analog for Gauss sums. It's really quite remarkable. At least the first time you see it. After some time, you might decide that this is natural from some point of view. At first, it looks really nice and mysterious. Okay, so the Euler beta integral says that gamma of A times gamma of B over gamma of A plus B can be written as an integral from 0 to 1 of x to the power A minus 1, 1 minus x to the power B minus 1. And we have to think of this as a multiplicative character times another one evaluated at 1 minus x. Okay, and then this might justify or suggest to consider the right-hand side of the next formula, which is the sum over x non-zero, maybe also x different from 1, in the finite field of a first multiplicative character times the second multiplicative character at 1 minus x. And based maybe on this analogy, you might guess, and then you might prove it's actually not very difficult, and it is the case that this is a product of two Gauss sums with the parameter which I had called A before fixed to be equal to 1, divided by the Gauss sum for the product of the two characters, okay, which corresponds to adding the two exponents in the complex gamma function. Okay, so we call J chi1 chi2 this Jacobi sum. Remarkably, I think I've tried to figure out when these sums were first considered, and the source I have at the moment, the oldest, is a paper of Jacobi from I think 1846. And what he really starts with is the left-hand side. So he seems to be starting with the analogy with the beta function. And then he expresses that as a sum of characters. Okay. We're going to see in the next slide a very beautiful application of Jacobi sums. I'm not sure if it was the motivation for Jacobi to consider them, but it's only a very beautiful application. But I want to say before that this analogy has led to lots and lots of other exponential sums and results. In particular, the very important hypergeometric sums of cats, which are very close analogs of hypergeometric functions in the very general sense. And okay, so the application I want to explain, and this is going to be almost a complete proof of a very beautiful theorem of Fermat, one of the earliest theorem really in algebraic number theory. And it states that if you have a prime number P, which is 1 mod 4, then you can find two integers, A and B, such that P is the sum of these two, the squares of these two integers. So P is A squared plus B squared. So it's something which is not true if P is 3 mod 4, just because you can look at the congruence mod 4 and you see that the sums of two squares of integers is never equal to 3 mod 4. But it's true for every prime 1 mod 4. So Fermat's original proof was probably by infinite descent, but Jacobi had or at least there is a proof with Jacobi sums, which is the following. So the first step, how do you use that P is 1 mod 4? Well, you observe that the multiplicative group is cyclic and has order divisible by 4. And from this, using the known structure of finite groups, finite cyclic groups, it's very easy to see that there is a multiplicative character chi2 whose image is exactly the roots of unity of order 2, so -1 and +1. So it's a homomorphism and it's surjective to plus or minus 1. This is actually true for any odd prime, but what requires that P-1 is divisible by 4 is that you can also find a character chi4 where the image is +i, -i, +1, -1. So surjective with 4 elements in the image, the roots of unity of order 4. Okay, now just look at the definition of the Jacobi sum as a character sum. It's a sum of products of values of chi2 times values of chi4. So it's going to be necessarily some integer plus I times some other integer. Okay, and you can compute in principle what A and B are by looking at how many times you get the various values of chi2 and chi4. So this is the first observation. Now the next observation is a computation which is not very hard and can be done in general. If the character chi is not always equal to 1, then the modulus of the Gauss sum squared is P. That's something you can also deduce from discrete Fourier inversion. And it implies, of course, in that case, if you apply the formula of Jacobi for Jacobi sums, so the Jacobi sum is a Gauss sum times a Gauss sum divided by another Gauss sum. So the modulus squared will be P times P divided by P. So the modulus square of Gauss sum is P, And on the other hand, it's a squared plus b squared, where a and b are integers. So we recover indeed the theorem of Fermat, and it looks magical because we seem to have found a formula for a and b by computing the Jacobi sum. In practice, this formula is not convenient because if p is very, very large, it seems we have to sum p different terms, but at least theoretically, it's a beautiful way to prove this theorem of Fermat. Okay, now another very important type of exponential sums over finite fields, maybe from certain points of view, the most important are the Closeman sums. So I want to define them. They look a bit mysterious at first. As usual, they might look a bit arbitrary. So it's normalized by putting 1 over square root of p. So this normalization is very important. I will explain later. It's related to the Riemann hypothesis over finite fields. And then the exponential sum itself. So the exponential sum in this case is over non-zero elements in a finite field. And then E of a rational function. So AX plus BX bar over P. So X bar is the inverse of X modulo P. A and B are 2 parameters, which can be in FP or in FP star. Let's say in FP star to begin with. It's simpler. Okay. Now, from the point of view of the analogy I described, if you are familiar with Bessel functions, if you think this as an integral with an exponential and then something of the form AX plus B over X, you would recognize that this is an analog of a Bessel function. And indeed, as for the gamma function, many of the properties for Bessel functions have analogs for Clusterman sums. So why are these exponential sums so important? Well, they occur in many areas of analytic number theory. Historically, the first time is they appear in the Fourier expansion of Poincaré series as computed by Poincaré in 1912. And this is the part of the really, really huge theory of modular forms. Interestingly, in this theory, the Closeman sums are really directly multiplied by a Bessel function. So the analogy is very clear. And then another source, another origin, independent origin for Closeman sums is in a paper of Clusterman from early 1920s, where he used them using a variant, a very deep variant of the circle method to compute the number of solutions asymptotically for the sum of AI times xi squared being some large integer. So where the coefficients AI are given, they are integers, positive integers, and the xi's are integral unknowns. So one can find the solutions or the number of solutions approximately using the so-called circle method. And to do this, one needs Clusterman sums. Okay. So now I'm going to start going in the direction of the topics I really want to discuss, in particular towards the end, which are related to the distribution of the values of exponential sums. So this is a story that maybe begins with a remarkable theorem of Gauss again. So what Gauss did in one of his proofs of the quadratic reciprocity law, he realized he had to compute what's called the sign of a Gauss sum for a character of order 2. So precisely, you take an odd prime p. As I said earlier, you can then show that there exists a character which has values +1 and -1. Both of them arise. And if you look at the Gauss sum for this character and value a equal to 1, it's not difficult using the computation I sketched before that the modulus squared is equal to p. So it's a real number times square root of p. And well, not necessarily a real number. So it's square root of p times something of modulus 1. And by computing the complex conjugate, it's quite easy to check that the sign epsilon p, what people call the sign, is either plus or minus 1 or plus or minus I. So it is a root of unity of order 4. And the really surprising fact, at least a posteriori, and a very tricky fact to prove, that was proved by Gauss in the early 19th century, is that in these two possibilities, the sign is always +1. So the Gauss sum is always either square root of p or I times square root of p. So it's always a solution of a quadratic equation, x squared equals plus or minus p, and it is always the solution which is in the top right quadrant of the complex plane. So this might sound like something relatively innocuous. It is quite difficult to prove, even nowadays. Of course, people have found relatively short proofs, but they're all very tricky. Gauss himself says in letters that it took him 5 years to actually compute this. So he found that this had to be true by numerical experiments. So it's one of the nice things about exponential sums of finite fields or other parts of number theories, that very often you can do experiments. So you can guess that certain things are going to be right. But sometimes proving these conjectures can be very hard. So in this case, even for Gauss, it's like a multi-year amount of work. Okay. Now, this is almost the only case I know where an exponential sum can really be computed exactly. Usually, we know certain things about these sums, but we cannot compute them exactly. So what I'm going to discuss now are the deeper theory of exponential sums, which shows that they always have certain type of structural properties. So they are not just completely arbitrary complex numbers. And these properties, as I said, are related to the Riemann hypothesis of a finite field. So they were first discovered in simpler cases by André Weil. And then it's the development of algebraic geometry in the 1960s, especially the work of Grothendieck and his school, and then culminating with Delin's proof of the Weil conjectures on the Riemann hypothesis of finite fields. So this is for an individual sum. Now, one thing you have already seen in the examples is that an individual exponential sum is not necessarily what we are really looking at. They tend to depend on parameters. So we had examples like Gauss sums depend on a multiplicative character and an element in Fp or in the finite field. Jacobi sums depend on 2 multiplicative characters. Clusterman sums depend on 2 additive parameters, so A and B in Fp or in Fp star. So, and these are the kind of families that you should think about when we look at all the possible Gauss sums, modulo P, or we look at all the possible Jacobi sums or all the possible Clusterman sums, varying the parameters. And then it was discovered by Delin in a certain case that these exponential sums, when the parameters are all in algebraic varieties, I will say a bit more later, always have regular statistical behavior. It's quite remarkable fact. Individually, they are kind of unpredictable, but their statistical behavior is very, very rigid. This was studied and expanded a lot by Katz, who also succeeded to show that such properties also hold for exponential sum parameterized by a single multiplicative character, using fairly different tools, as I will mention. And then the work that I'm going to talk towards the end, so in progress with Arthur Fauré and Javier Frezan, we are generalizing this to other types of parameters, like more than one multiplicative character or a mixture of an additive and a multiplicative character. Okay, so let's consider first these structural properties. So one should think of these as being the properties which are true for a single exponential sum. And I illustrate them on one of the simplest examples, the exponential sums with an additive phase given by a polynomial. So again, there's a normalizing factor, 1 over square root of p, which will be explained in this slide. And then the exponential sum has e of f of x over p, where f is some polynomial. And for simplicity, I assume its degree is strictly less than p, just so that certain statements later are not possibly false. So what André Weil proved, and this is the Riemann hypothesis for curves over finite fields, is that you can always find d minus 1, d is the degree, algebraic numbers, alpha 1 up to alpha d minus 1, so complex numbers, such that first the sum normalized by the 1 over square root of p is the negative of the sum of these alpha 1 up to alpha d minus 1. So this sign is kind of a convention, but it also has good theoretical justification, so that's why I put it in. And also these numbers are of modulus exactly 1. which is a form of the Riemann hypothesis over finite fields. And the corollary that one deduces is that normalized by the 1 over square root of p, the exponential sum is bounded by d minus 1, which is something that you can prove elementarily if the degree is either 0 or 1 or 2, but that becomes hard even for degree 3. It's really non-obvious. Okay. So this is for the special case, and more generally, essentially every exponential sum will have similar structural properties. So there might be more terms. You might have to combine terms which are not always exactly of the same modulus. There might be some degeneracies. The normalization might be different than 1 over square root of p, but you will always have an expression of this kind. And the alpha i's are not necessarily completely explained by Weil, but they become very transparent in the Grothendieck-Deligne approach in terms of étale cohomology. Okay. And one interpretation, which is at that point is formal, would be to say that the exponential sum is minus the trace of a unitary matrix of size d minus 1 by putting these alpha i's as eigenvalues. And this turns out to be the key to the distributional properties. So the distribution properties, so if I want to summarize relatively quickly what Deligne proved in the early 1980s. So as a slogan, this is not a formal statement, of course, but essentially any family of exponential sums, provided it's parametrized by an algebraic variety. So here you should think of the Closeman sums with 2 parameters which are free in FP, but you should think of not multiplicative characters. So multiplicative characters are not allowed by Deligne's theorem. So any such family will behave statistically as if, on average, the value of the sum is the trace of a matrix taken at random, uniformly at random, in a certain compact group, which is given in some unitary group of a certain size R. So in the example I had before, for SFP, R would be d minus 1. Because we had sums of that many elements of modulus 1. Okay. What Deligne does not tell you, and this will be the topic of the end of the talk, is what is this group capital K? So Deligne tells us there is always an a priori form of statistical distribution, which is of a very specific kind, depending on some compact group. But it does not tell us what is the group, because this, of course, is going to depend on the exponential sum. Okay. And there's a technicality, which is that in principle, the statistical variation should be when you vary the base finite field. But I don't want to go into this technical point. Now, for the proof of this, the key tool was Deligne's proof of the Riemann hypothesis of a finite field in its strongest form with all the attending formalism. So it's a really spectacular result obtained as a consequence of even more spectacular developments that Deligne achieved in the early 1980s. Let's illustrate this on the case of Clusterman sums, which is a very good illustration. So in this case, André Weil had shown that the parameter R, so the number of elements of modulus 1 that you add to obtain the normalized Clusterman sum, is 2. So in other words, the Clusterman sums are the traces of certain matrices belonging to, in principle, U2 of C, but one can show the determinant is 1. And so they are distributed according to the trace of some compact subgroup of SU2C. And it was Katz who proved that the compact group capital K in that case is equal to SU2C. So in other words, the Closeman sums behave statistically like the trace of a random matrix taken in SU2C uniformly at random. And this has a very concrete expression because the trace of matrices in SU2C has a law, it's a real number between -2 and 2, and the distribution is given by the measure, which is 1 over pi square root of 1 minus t squared over 4 between -2 and 2. So the Deligne-Katz theorem in that case says that whenever you take a continuous function from -2 to 2 with values in C, and if you're interested in computing its integral with respect to this measure, which corresponds to the trace of a random SU2 matrix, you can recover it as the limit of the average of the values of F evaluated at the Clusterman sums. So where you sum over A and B in Fp star. Limit as P goes to infinity. So this is the kind of statement we mean when we say that family of exponential sums has a certain statistical distribution. And in this case, the computation of the group capital K was not too difficult, but for more complicated exponential sums, it can become a really challenging problem. Okay, but before I discuss a bit this question, I want to discuss the generalization that Katz obtained in 2012. So he basically proved that the universal equidistribution theorem of Deligne, which was proved by Deligne for families parameterized by algebraic varieties, also holds when you have families parameterized by multiplicative characters. So for instance, here I wrote down a simple case where again you have a specific normalization, and then the chi of x, that's the parameter, a multiplicative character, and now the exponential f of x over p has a fixed polynomial f. So for instance, e of x cubed plus x over p. And you look at this when chi varies. So Deligne theorem just does not apply at all in this case for completely fundamental reasons. But Katz, in an absolutely remarkable work, managed to extend the theorem, the equidistribution, by relying, first of all of Deligne's work on the Riemann hypothesis of finite fields. And then he introduced a new ingredient to construct the group capital K, which governs the equidistribution. And this was the use of Tannakian categories, which was brand new in this context. But this is a formalism which can allow you sometimes to construct a group a little bit like a Galois group out of very abstract properties of the exponential sums, which in this case are related to the fact that we are computing the analog of a Fourier transform over the multiplicative group of a finite field, and these satisfy convolution formulas. And it's the convolution formulas which are the key to obtain this Tannakian formalism to apply it. Okay, and so in this work in progress, which we hope to finish, at least to have a first draft relatively soon, so Arthur and Javier and I, so we succeeded in extending this universal equidistribution to all families parameterized by the characters of an arbitrary algebraic group, commutative algebraic group. So concretely what this means, so is that we can look at a multiplicative and additive character, like these sums here, which are like Closeman sums, but also with a multiplicative character. So chi of x, e of ax plus x bar over p. So if we fix chi, this is a family that Deligne can treat. If we fix A, we can use Katz's theory. If we want to view this genuinely as depending on two parameters, we need this new theory. Or we could have two multiplicative characters or three multiplicative characters, and so on and so on. And we can have abelian varieties also if needed. So this is based on the approach of Katz. So it starts, of course, with Deligne's work. We always rely on the Riemann hypothesis of Deligne. We rely on the ideas of Katz. So we construct Tannakian categories to construct the group. But then because we have objects essentially of dimension larger than 1 in comparison with Katz, there are some highly non-trivial arithmetic or algebraic geometry that occurs related to vanishing theorems for cohomology, which has been studied in different contexts for different purposes, for instance, by Weissauer, by Kramer, and other people. And then the crucial arithmetic new tool that we need, in addition to this, is a very recent development of Wilsawin, a development of a quantitative version of shift theory on algebraic varieties over fields, especially over finite fields. So Kronecker is well known in number theory to have had a Jugendtraum about a class field theory. So this quantitative shift theory, I think for Philippe and I, was very much maybe not a Jugendtraum, but a Mittelaltertraum. So I think it's been at least 10 years that we've hoped that such a theory could exist. And it's only in the last 2 years that Will Sawin has managed to construct it. And I think it's going to be one of the most essential tools in the analytic study of exponential sums in the next year. So for us, it's completely crucial in making our arguments work. Okay, and so once we've done, in some sense, the foundational stuff, so we obtain, as I said, the analog of the Lin theorem. So basically, where you're given an arbitrary family of exponential sums parameterized by characters of a commutative algebraic group, we know there is some equidistribution property. And the question becomes, what is the group? How is this a concrete equidistribution? So in other words, the analog of computing SU2 in the case that Katz did for Clusterman sums. And this is a highly non-trivial question because even for the Lin theory, where in some sense this group is given almost concretely, it's the image of a certain homomorphism. So you could say, well, you compute the image. In this case, it's given by this very beautiful but very abstract formalism of Tayankyan categories. How do we compute this group? So there are not too many tools. There is one which I want to discuss. It's really wonderful because it goes back to the very definition of the exponential sums, and it's extremely concrete, and it seems miraculous. So it's called Larsens alternative. So it's a result that was discovered by Michael Larsen, I think in the early 2000s. It was developed extensively by Nick Katz between 2000 and 2010, and it takes the following form. The remark is that, so we want to compute this compact group capital K. What we know is that it's given in some unitary group, and we usually know the value of the integer R. Now, Katz and Larsen observe that very often by using the definition of the equidistribution, the abstract universal equidistribution, you can compute the so-called moments of this group, which are the averages with respect to the uniform measure, probability measure on the compact group K of the modulus of the trace to the power 2m. So the trace means we view elements as unitary matrices. Okay. This is done by typically, as in this example. So here I'm looking at a family parameterized by an A and a chi, so a 2-parameter family. And the force moment in that case, so m is equal to 2. So the average of the force power can be computed by taking the average of the exponential sums. So if you just expand this force power, you exchange the order of the sum. You use a funny property of independence of addition and multiplication, which is known as the Sidon property in additive combinatorics. And you show that the limit is equal to 2 when p goes to infinity. From this, the equidistribution is going to tell you that M4 of K of this group that we look for is equal to 2. And then this wonderful result of Larsen, almost, it could be that K is a finite group, but if it's not a finite group, it has to contain the whole unitary symplectic, unitary SUR of C, so unitary matrices of determinant 1 for the given integer R that you had found at the beginning. Okay. So out of a very simple numerical invariant that you can compute in a number of cases, you show that it's equal to 2, and you immediately deduce that the group capital K has to be essentially gigantic. So you then have to compute the determinant, which is somewhat easier, and if you can compute the determinant, then you can deduce, let's say, that K is the whole unitary group, which would be the target in many cases, or at least it determines K in many cases. Okay, so I think I have 2 more slides, but going through them might go a little bit over time, so I will stop here and thank everybody for their attention.